So hello everyone, thank you for giving me the opportunity to talk to you today. My name is Chad Briddon. I'm a third year PhD student at the University of Nottingham, working under Claire Burge and Adam Moss. Today I'll be talking to you about the code that we've been developing called SELCIE, which hopefully will help people calculate solutions for screen scalar models. Specifically for this presentation, I'll be talking about the Chameleon. So first, a summary and just some motivation for why we're interested in the Chameleon model. So as many of you are probably aware, you'll all be aware of this, dark energy makes up about 70% of the energy density content of the universe today and is responsible for the current accelerated expansion rate. However, what the actual dark energy is still a debated topic. One theory is that we suggest that it's a scalar field. These are called quintessence models. That has been frozen to some particular value, hence why it behaves as a constant. So the problem with these types of models, however, is that if you allow your scalar field to couple to matter, either directly or indirectly through gravity, this scalar field would then become a propagator for a new fundamental force. This is where the term fifth force comes from. And there have been many experiments looking for such fifth forces, and so far none have been detected, which puts strong constraints on the coupling strength of this field. This is why a lot of people have started looking at screen scalar field models. So these are scalar field models where the behavior of the field changes depending on the environment, allowing them to avoid constraints that are mostly relegated to regions like the Earth and solar system. So talking about the Chameleon in particular, the Chameleon has a somewhat unusual potential of this form up here. I don't know if you can see my mouse, but it's the first square. Has a form capital lambda over 5 to some power n. So n is just an integer and lambda is the energy scale. Solving for the non-relativistic static equation, we have the equation in the blue box. Here, rho is the local matter energy density and m is the coupling strength. And this is just a Klein-Gordon equation. So the right-hand side is the first derivative of some effective potential. So by setting this to 0, we can then find the value of the field that minimizes its effective potential, which I've written here as phi min. Using these two facts, we can then work out the mass of the field at this minimum value and its corresponding Compton wavelength, which I've written here. So when I refer to the Chameleon mechanism, specifically the fact that this phi min and the Compton wavelength are functions of rho. So as you notice, as rho will increase, the Compton wavelength will decrease. This means that fifth forces will be suppressed. So you can imagine that in regions of relatively high density, like on the surface of the Earth and solar system, where most of our constraints come from, the fifth force will be suppressed because of this. Whereas on larger scales, where rho is relatively smaller, it's less suppressed, and so the field can propagate these fifth forces. So the problem with the Chameleon and other screen scalar field models is that in order to get this screening behavior, we now have nonlinear equations of motion, which are very difficult to solve. So here I've given some examples of approximate analytic solutions to this equation. So how these equations are constructed is you make various approximations in different regions of space around symmetric sources and effectively stick those solutions together. The problem with that is that these are only valid for specific areas of the parameter space. Another problem is that they don't really give you any information about more general solutions. For example, below, I've shown there's an example of a shape derived from Legendre polynomials. And from these pre-existing solutions, you couldn't really figure out the solution around this shape. And so you wouldn't really be able to do any experiments with it. So that's where our code comes in. So our code is called SELCIE, stands for Screening Equations Linearly Constructed and Iteratively Evaluated. It's very much says what it does on the CAN type code. So the idea of this code is that if you're interested in a Chameleon model, you can then use this code to construct a system that you're interested in, and it will solve the Chameleon equation for you, which you can then base your experiments around the results. To give credit where credit's due, there are two pre-existing software that the code utilizes: GMSH for the mesh generation and Phoenix for solving and evaluating the finite element method. So here I've written an example just to demonstrate how the code works. So say, for example, you're interested in this type of horseshoe shape inside of a vacuum chamber. So the entire code works in 3D or 2D, but if it's in 2D, you need to add some symmetry. So just imagine this mesh kind of coming out of the page at you. And so how you'd go about using it is you can define some shape. Here I've used a function called horseshoe that just returns a list of lists, and each sublist is the XYZ coordinate of a point. And how the code interprets this shape is it just connects those points in sequence to give you this horseshoe pattern. But this can be any function that you can define to make a continuous shape. I then define it to be a subdomain with this third line. This means that when I set my density profiles, it only affects this one shape. If I added other shapes, I could then group them together as one subdomain. I can also control the refinement. This is very important for these type of models because often most of the variation occurs close to the boundary where the change in density is quite sharp. And so by controlling the refinement, as you can see on the mesh, the refinement is very fine near the boundary where most of the computation needs to be, and less fine in the vacuum where you expect the variation not to be too much. So that way we save on computing time without sacrificing precision. I then this next line just places it inside a vacuum. And again, I can define what I want the mesh to be doing around the edges of that vacuum. And I can just define some wall. So now we have, this also creates two new subdomains. So now we have 3 in total. And then I generate the mesh and save it. So now we have some file with our mesh saved. Now we go about solving it. So the most important thing is the density profile here on the sort of second section. So here I give it the name of the mesh that we're using and the dimension and the symmetry. As I said, this is a symmetry of it coming out of the page at you. And then I can define the density profiles. So these are arbitrary functions that take in some position vector and return the value of the density at that position vector. So for this example, these just return constant values. So the source and wall are 10 to the 17 in our rescaled units, and vacuum by definition is 1 in our rescaled units. But I'll explain on the next page how general these can be. So we've defined the system. We then define the field solver with our parameters. Here, n is the same parameter as before. Alpha is a value that comes about from how we rescale it. So basically, when you rescale the Chameleon equation, it becomes a 1-parameter problem, that being alpha. Physically, this is just related to the Compton wavelength squared of the field in the vacuum.
2 minutes.
Thank you. We then set about using, there are different options. Here I've just used the Picard iterative method, and after a few iterations, the Chameleon field has been solved. From here, you can do lots of things. You can plot it, as I've done on the right. You can calculate the field magnitude, the magnitude of the field gradient, which is going to be proportional to your fifth force and equal to fifth force once you introduce your dimensions. And here I've also plotted that, and I've just marked a little X to show where I've probed this value. So just to demonstrate sort of the type of things you can do if you're wanting to know about this system. So I mentioned that before I just used constant densities. Here I just wanted to demonstrate how general our method is. So here I've got 2 systems of various subdomains of different sizes embedded in one another. And each one can be set its own density profile completely independently. So here I've got some that vary as functions of R, some as functions of X, some as constants. This is just to demonstrate how general everything is. So for example, if you had some galaxy cluster data and you write a function where you give it XYZ coordinate and it returns the mean density in that region of the galaxy cluster, you could just input that as into your one big subdomain and it will calculate the Chameleon field. So very quickly, just to go over what we're working on and what we hope to do. So we're still actively working on the code. I'm currently using it for shape optimization for laboratory experiments. We're also hoping to improve how the generality of it, so introduce things like Newman boundary conditions that the user can input. At the moment, this only works for the Chameleon. However, the hope is to make it more general for screen scalar field models. So people in our group are currently working on making a Symmetron version. We're also hoping to add time dependency. So far, everything I've talked about was for the static case, but in the future, we hope it's to be so that the user can have the input a system that evolves in time, and the field is time dependent, so takes in that evolution into account. Thank you very much for listening. If you're interested in this work, the archive paper explaining the code and examples that we use to verify it is here. Also, the GitHub repository if you want to have a look at it yourself. Any questions?
Thank you very much, Chad. I think in the interest of time, we'll defer the questions to the chat or the Slack